So with this, I welcome all of you to the special edition of the RISC-CAN webinar series on compound extremes. The webinar series is part of the RISC-CAN initiative, which is sponsored by WCRP, IRDR, and Future Earth. The working group that is organizing this webinar series is chaired by Colin Raymond, Marcus Reichstein, and me. This is a monthly webinar series. The next one is already scheduled for June 30th. We will have Michael Puma speaking on COVID and risks to food security. And we will have an additional speaker who will be announced then. If you're interested in RISC-CAN in general and want to be notified in time by these webinars, then just go on the RISC-CAN webpage, which is risc/can.org, and you will find all the details there. Today, it is our pleasure to host the EGU session on compound weather and climate events, which is convened by Jakob Seichler, Nina Ridder, Bart van den Hoek, and Seth Wester. And with this, I will pass the digital mic to Jakob, who will give you a short overview about today's seminar and how we plan to do talks / questions and comments.
Thanks, Kai. Hello also from my side. This is the second part of our online EGU session. Maybe you have already participated in the sharing EGU, where you could only chat with each other but not really talk. So after yesterday's first 3 talks, today we have another set of 3 talks. One by Alois Tilloy on spatiotemporal features of compound wind and precipitation extremes in the UK. One by Freya Gary on multiple hazards under UK climate projections, the future of UK agriculture. And one by Mohamed Reza Najabi, non-stationary compound weather extremes in Canada based on large ensemble climate simulations. Each speaker will have about 15 minutes for the talk, plus 5 minutes for questions, so that we have about 20 minutes per speaker. And I would like to draw your attention also on 2 special issues that we currently are running on the topic of compound events. One is in the journal Weather and Climate Extremes. It's the special issue on compound weather and climate events, and the deadline has just been extended to end of July this year. So if you want to contribute to this, you have another nearly 2 months. This is more for papers really on the climate and weather domain. And then another special issue that has started in March is an interjournal special issue in the Copernicus journals, which are also hosting EGU usually. And this is in biogeosciences, earth system dynamics, hydrology and earth system sciences, and natural hazards and earth system sciences. And here the deadline is next year in February for the submissions. And this is also then for compound events and impacts. So depending on what topic you research on, you can choose the journal that is the best fit. So without further ado, I would then invite the first speaker, Alois, to start his talk. Alois is at the King's College in London. So I will stop sharing my screen. And unmute Alois.
Okay. Thank you. Thank you, Jakob.
And while Alois is preparing, so for the questions, you can either raise your hand in the Zoom with the Zoom features, or you just type your question in the chat, and then Kai or I will pick it up and then give you the mic or give the question to the speaker. So Alois is ready. 15 minutes.
Okay. So hello everyone. So today I'm going to present you some of my latest work for my PhD in King's College London about compound wind and precipitation extremes in the UK. To give a bit of context about my research and hazard interrelation in general. There are different aspects about multiple natural hazards and their interrelations. And in my work, I looked at three main aspects. So how do hazards relate, which has been a topic of a paper we published, which was published last year. How to model these interrelations. This was a topic of a second paper, which is still under review. And our topic of today, which is I've been looking at the scale of interactions between natural hazards, and in that case, in particular, between wind and rainfall extremes in Great Britain, with the idea to look at the probability of occurrence of these events and their duration and spatial extent. So first I will introduce what I mean by compound hazard in space and time. Then I will present the methodology I created to identify hazard event and compound hazard event. And then we'll see the results of the study. And I want to also say that this approach is aimed to be applicable to different natural hazard interrelations, not only wind and rainfall, but it depends more on the data availability than on the hazard. Compound hazard, it can be defined as two or more hazards occurring at the same time and place. But natural hazard can overlap in various ways on different time scale and impact various sites. So, for example, on the two images, you can see like idealized representations of two hazards. For example, the wind in orange and the rain in purple during a storm. So an hazard event is therefore, I define it therefore as a cluster. So, for example, this purple cluster, footprint, which is depend on a singular phenomenon. So in space and time, it's possible to define compound in different various ways. So I made this small table with to show that you can define a spatial overlap as overlap where both hazards occur, or the spatial domain, let's say, or with the whole combined footprint of both hazards, and the same with time. And in that study, I choose to use only the overlap of both hazards in space, but during the aggregated period. So the image number with small a in the figure on the right. So as I said, I've been looking at extreme wind and precipitation with ERA 5 climate analysis data over the whole range of available data, so from 79 to last year, with a temporal resolution of 1 hour. And I extracted two variables, which is the total hourly precipitation and the maximum hourly wind gust. So my domain is more or less Great Britain, with a guard area around it, which is the red rectangle. the idea of this area is to mitigate the edge effects during the clustering procedure. And the first step of this procedure is to select extreme events which can be proxy for hazard. So in that case, I set 99 threshold at the 99th quantile for each cell. So this threshold varies spatially. So I did this procedure for wind gust and for wind and for precipitation separately. And so then with these extreme events, which are points with coordinate in space and time, I've been clustering these events with clustering algorithm called dbScan. Basically, dbScan I chose dbScan because it can create cluster with arbitrary shapes, which is good in my case because I didn't have any big assumption about the shape of the clusters I wanted to create. And it does not require the determination of number of clusters prior to the clustering, which was also a good point. So then events in a space-time cube are then clusters, and to create hazard events, which therefore, I look at the overlap of rain hazard event and wind hazard event to create compound hazard events, and I give and each of these single or compound hazard events has intensity and scale attributes. The intensity attributes are like rain accumulation, so it's the sum of the rainfall in each grid box or cell during the whole duration of the event. And the wind accumulation is the maximum hourly wind gust in a cell during the event. The spatial footprint is measured in percentage of the study area, the duration in hours, and I also extract the location of the event center, which is either the maximum location of maximum wind or maximum rainfall. As an example of output, this is so the footprint of storm Angus, small a in the map A, and a consecutive storm which occurred just 46 hours later in B. On these maps, it's possible to see the intensity of both hazards, their footprint, and also where they overlap and where they don't overlap. The good thing as well is that the clustering procedure managed to separate these two clusters into and not create one big cluster with the two storms. And here the footprint is in agreement with this observation. And to go further with this kind of confrontation with observation, I selected 15 past events which occurred in Great Britain between 2009 and 2019. Among them, 7 rainfall events, 3 extreme wind events, and 7 compound events. And I compared cluster attributes, so intensity and scale attributes, with observations from Metofis, but also from other sources. And finally, the main result is that the method underestimates the rainfall accumulation, but accurately catches wind accumulation, maximum wind accumulation value, also the duration, and even if I didn't find any quantitative measure for the spatial scale of the 15 events, the spatial scale is also well catched by the clustering algorithm. So now going to result. First, I looked at the number of hours, average number of hours per year in a compound hazard event to see which areas of the UK, of Great Britain are most, let's say, impacted by these compound hazards. So in that case, it's the southwest coast of Great Britain, and there is a strong west-east gradient with like much more occurrence of compound hazard event in the west than in the east. And on the figure B, this figure shows the likelihood multiplication factor, which basically shows the influence of the dependence between wind and rainfall event on the estimation of the average number of hours per year in a compound event, which is over the figure I just presented. Basically it shows that even if there are not as many compound events, for example, in south east of England, when a wind event occurs, it's really it's more likely than a rain event will also occur in that place than in, for example, in the Midlands. Then I looked at the seasonality of single and compound hazard events. So on the figure, you can see a box plot of monthly occurrence of these events. So compound event occurrence follows more or less the wind event occurrence, and there is a strong seasonal signal with a high season in the extended winter from October to March, and a low season in the extended summer, with 82% of the events occurring during the extended winter. To go further with the seasonality, I looked at the proportion of compound hazard event among all events, so wind only plus rain only plus compound. There is again this pattern of high and low season, and this means that during the winter there are more compound hazard events, but their proportion among all events is also greater, suggesting that there are some conditions leading to this type of events that are more likely to happen in the winter. And also, we can see, it's possible to see on this figure that there is an important annual variability between in monthly occurrence of proportion of compound hazard events. Finally, I looked at the intensity of these bivariate intensity of these events. So here you can see a scatter plot of all the compound hazard events detected, and the blue curve is a joint exceedance level curve which has been drawn with empirically with a kernel density estimator, and it represents more. It's supposed to represent a 1 year return period event for this data set. So I used the joint tail model to first estimate the return period of the event above this curve, which are 222. And also I used the joint tail model to measure the dependence between rainfall accumulation and wind accumulation. And there is a weak positive dependence, but in that case, also the two rainfall and wind seems to be asymptotically independent. When you go far in the extreme, they seem to be independent. And finally, I looked at the influence of this of the intensity of compound event on their scale attributes. So on that plot, you can see so all the compound hazard events are represented with their duration and spatial footprint in gray, and only the major 222 major events in colors, with colors representing their estimated return period. What I can say is that these major events tend to be larger and last longer. So the intensity of wind and rainfall has an influence on the duration and the footprint of compound hazard event. To conclude, so in this work, I created a database of more than 4,000 compound wind-rain clusters over Great Britain. And the occurrence of these events are dependent, like, so wind and rain events are dependent in their occurrence, but there are strong spatial and seasonal variabilities. Within events, the intensity of wind and rainfall are asymptotically independent. And major compound events with a high return period have on average larger footprint, spatial footprint, and last longer. And that's all. Thank you.
Thank you very much. This is very interesting analysis. Are there any questions from the audience? So you can either type in or you can unmute yourself and ask.
So I could kick off the questions maybe. I was wondering what the joint damage function of wet and windy extremes would be. Like for hot and dry, it seems to be that they just affect crops a lot. For like humid and hot, it's really dangerous for health. Is there one key example where wind and wet extremes are particularly problematic? I guess storm surges would be one, but is there one general other?
You mean like an example of, let's say, a negative impact on like society or something like that?
Yeah, like what would be the key motivation to study?
Yeah,
wet and windy.
I've been working with an energy company, and I think their the motivation behind is more impact to infrastructure, and having both the extreme rainfall and maybe therefore flooding and extreme wind can first damage, create, like, let's say, cascading damage on infrastructure, but also slow down the, let's say, if there is damage and too much wind, you know, the kind of the safety, people cannot go out, and they have a lot of, they have some issues with this, so they wanted to know.
Thanks.
Are there other questions? I would also have one. So we are talking about this, that your clustering underestimates the rainfall for these bigger events. Couldn't this be just an effect of the data set? Is it, so do you know how well ERA 5 simulates rainfall extremes?
Yeah, I think it's partly due to the data set. From what I read is, I think ERA 5 was like the less bad data set to do this kind of thing. But yeah, I think it comes from the data set, of course, and maybe a bit from the clustering method, because I take only the 99 percentile, so maybe I can miss some of the rainfall, like small amount of rainfall also occurring. But yeah.
Any other questions? There's a question from Roberto. Do you want to
I need to open the
take it yourself? Otherwise I can. He's asking, related to my question, did you test other rainfall totals, like 3 hours, 12 hours, or 24-hour totals?
Yeah, I tested to do like kind of moving sum. So like at each time step, I had not the 1 hour rainfall, but a sum of 1 hour and the hour before and hour after. And yeah, it has an impact, but yeah, more on the number of events than on the value itself of the precipitation. But it doing this is like doing a pre-clustering, because you already cluster give more weight to moments where you have several hours with intense rainfall. Welcome.
Thanks. Okay, I don't see any more questions. So Freya has already started to share her screen.
Okay.
So then we move on with Freya's talk on multiple hazards under UK climate projections. Freya is at the Met Office, also in the UK. The floor is yours, 15 minutes. Do you need to unmute you?
There we are.
Okay, now we hear you.
All okay, great. Okay, so in this talk, I'm going to provide an overview of some of the content I've been doing over the last year, focusing on UK agriculture to start with. So I'll just quickly mention the large project that I'm funded by. So the Strategic Priority Fund for UK Climate Resilience has got a big picture remit in the UK to enhance resilience through traditional hazard research. So for example, improving extreme value theory, right through to multidisciplinary projects with direct engagement with community stakeholders. So there's a lot of different projects in it, but one of the projects within the Met Office is on multiple hazards and future UK risk. And that's my work. So that adds to two of the main objectives of the project, really, focusing on the characterization of the risks, but also managing those risks through adaptation. So a key part of our approach is not just understanding the hazards, but also thinking in terms of a risk-based framework. So effectively drawing in that understanding of vulnerability and exposure to a hazard in an area. So as such, we've really been trying to reach out and learn from people about the key questions and concerns that they have in their sectors. So of course, you can then look at that same diagram from a compound risk perspective. So as well as the climate event that may be extreme in multiple meteorological variables or in a temporal or spatial sense, we know that in reality, compound risk is going to be informed by non-climatic drivers as well. So I think it is really important for us to talk about that and there to be multidisciplinary research bringing all that together. However, as we know, it's still quite an early field, really. So initially, my qualitative research will be characterising the projected changes in risk just from the climate hazards over the 21st century and assuming that the non-climatic drivers are remaining constant. So as most of us, I'm sure, are well aware, compound events can be really complex. Firstly, in terms of their varying timescales, which can be extreme and instant or prolonged over months. And I'm going to talk about two case studies of that today. So they may involve a very extreme or rare component, a so-called black swan event, but also compound events may have severe impacts because of the combination of hazards and impacts, and the initial hazards may not be especially severe. So the same climatic event may well hit multiple sectors simultaneously, and events in one sector, so the energy sector, may well then trigger and amplify effects in other sectors as the power is disrupted, for example. So at EGU, this philosophy of Heraclitus, effectively, you'll never step in the same river twice, was mentioned a few times, that compound events especially are highly likely to be unique and with local impacts. So as such, more traditional methods of climate scientists, which are typically more large-scale area assessments of risk, may not be ideal for local planners. And the science may be presented in a way that's difficult for planners to interpret or use. So in this work, we're focusing on more local research and using case studies. However, of course, as the philosophy indicates, lessons from the case study itself may not be broadly applicable, but the methodologies that we're developing to examine future projections of multiple hazards hopefully will be. So we're going to build a publicly available code base, which hopefully others then can use to look at different combinations. So to further comment on the stakeholder side of the project, what we found so far across sectors is an acceptance of the likely growing importance of multiple hazards over the 21st century. But it's typically not well quantified by stakeholders yet. The compound events field seems to me, actually, as we were talking about just in the introduction, it's an intersection of several communities, the climate modelling community, of extreme events community, and the advanced statistical communities. So some sectors have practitioners with more understanding and experience in these areas than others. So the agricultural sector specifically is considered to be a UK sector needing more action on climate-related risks. So initially that's why we focused in on it. But the idea is for us to develop case studies across a range of UK sectors and with engagement to stakeholders themselves, so that we can create products that are useful for them and communicate in a way that they understand. And obviously, from a climate research background, it is becoming increasingly clear to me just how time-consuming developing that stakeholder relationship part of the project can be. So just to give a quick overview of the UK agricultural sector, a few facts and figures. The impact of extreme weather is already being felt by farmers, and we've a mix of crops and livestock, lots of outdoor grazing sheep and cows, the meat from which are key exports from the UK. The agricultural sector is also a large employer and particularly dependent on migrant workers. So here are some of the ways that we've tried to establish what are some of the key challenges for UK agriculture and how these might develop under climate change this century. We've some experience in agriculture already within the Met Office, and we've built links into several different governmental type agencies who have more experience of developing science into policy. I've also actually found agricultural news to be a key source of understanding concerns, and now climate change is increasingly in the news agenda. There's more surveys and things like that that can give more information about farmer experiences. So our approach is to look at a number of case studies and create methodologies that can be applied elsewhere. For those not familiar with UK climate, we've a wetter west coast, as most precipitation comes from the west in maritime air masses and falls on the higher topography along the west, as well as the summer average temperatures being over 7 degrees warmer in the southeast than the northwest of Scotland. So there's thresholds or risk indicators that have already been established that we can draw into our work. However, in some cases, it requires considering past compound events and their impacts to generate our own thresholds to be able to assess changes in risk for similar types of events. So there's a number of different types of climate projections in this product, the UK climate projections, which ranges from global projections using state-of-the-art global high-resolution climate change simulations at 60-kilometre resolution to regional projections at 12-kilometre and 2.2-kilometre resolution. So there's also probabilistic projections, which include much larger ensembles of a Hadley Centre model and information from CMIP5 models, but they're not as spatially or temporally detailed as the regional projections. So looking just at the regional projections at 12-kilometre and 2.2, so today actually I'm only going to show results from 12. We're able to look at relatively local scale. For each resolution, there's a 12-member perturbed parameter ensemble. So each model's parameters are plausible but different, and this leads to different projections and encompasses some model uncertainty in the projections, although the ensembles use just one model. We're looking at multi-decadal changes in hazards out to 2080. So beyond 2050, we expect emissions forcing to have a significant impact on projections. And this ensemble is using the RCP 8.5 emissions scenario. So it's a high-end projection, but it's certainly one that adaptation on these timescales may wish to consider preparing for. So here I'm just going to consider these extreme events I'm going to talk about today in the framework of Schleichler et al. So with the articles currently in press, as I understand it. First, we consider a case with multiple variables. So for this, I'm going to show an example of heat stress in livestock, which that index includes both temperature and humidity. Then we're going to consider a preconditioning event where previous event from one driver means the impact from another later driver is magnified and becomes extreme in terms of impact. So I'll show a cold spring followed by a warm summer example and explain why that's important. So the large spatial extent of that latter event actually increased that impact, so it could also be considered a spatially compound example, and not related to agriculture, but just to mention another famous UK-based temporally compound and high impact event was the destruction of the railway in the southwest of England, close to where I live. And the repeated storm surges over winter there eventually caused the wall to collapse. But the final surge was not actually the greatest one. And of course, coastal impacts are obviously very much of interest in the UK. So in 2018, we had a very hot, dry summer. You can see there the temperature and rainfall anomalies compared to climatology. So in general, wheat yield was down due to the climate conditions. And of course, there's a very high cost of energy and water if farmers are trying to mitigate that. The conditions were exceptional because they were so widespread. And of course, if you get a deficit in agricultural yield within a country, then additional imports can make up the deficit. However, if climatic countries for the countries of import, primarily for us, that's France and Germany, also suffer extremes as well, that can increase the severity of the impacts. So the hot, dry summer of 2018 was preceded by a cold, wet spring. This meant that livestock were kept inside for longer and they have to be fed. So when the weather is good enough, cows are put outside where they can eat the grass. However, quick transition to hot summer, the quality of the grass deteriorates, the livestock are put under heat stress. So the cattle in many parts of the country have to be brought back indoors and need feeding. So there was a crisis of livestock feeds being in very limited supply and getting very expensive. And in addition, being inside and not eating fresh grass for much of the year does expose cattle to health risks. So to consider this problem of the cold spring followed by the warm summer, I'm assuming spring, February, March and April. And considering if the monthly average for each of these months is less than the criteria for cold spring months, which I define as a certain amount below climatology from the 2018 conditions. I do the equivalent for the warm summer months of May, June, July. For just one ensemble member, I here show for illustrative purposes when cold spring and warm summer events occur in the projection. So if there's one cold month in the spring, then there's an index of 1, 2 cold months, 2. So as you probably guessed, there's fewer instances of cold springs further into the future, but hot summers become common. So I'll just add that all the results I'm showing today are preliminary results using the raw model data and they're not yet bias corrected. So we calculate the probabilities over 10-year periods of both a cold spring month and a warm summer month happening in the same year and show these as a spread across the members of the ensemble and then for 2 months and 3 months. So you can see that between 2020 and 2040, one cold month and one warm month in the same year may happen up to every 3 and 10 years. So events which are slightly less severe in terms of duration than in 2018 are still something that you might want to prepare for. Events similar to 2018 in terms of magnitude and duration, where there's 2 cold and 2 warm, maybe up to a 1 in 10 year event. But you don't see any instances of 3 cold spring months in the ensemble, so there's no probability shown there. So to look at a different type of example on daily timescales, we show this example of thermal heat stress on livestock. So this is a daily index using temperature and relative humidity information, a multivariate event. Some heat stress decreases your weight gain, fertility and milk yield from your cattle. And obviously then extreme heat stress could lead to mortality. We here show the results for the southwest of England. So that's where the Met Office is based, but also where there's 1.7 million cows, a very densely populated area, and very vulnerable to this hazard. It's a high risk area. So for each of the ensemble members here, we're showing how many days per year are above a threshold for heat stress in a baseline climate period of 1981 to 2000 in blue, and in a future climate period of 2061 to 2080 in red. So as you can see, for all of the ensemble members, there's a big difference between the baseline and future period. In the future, there may be nearly 2 months each summer where livestock are stressed in the southwest, as per this index. So there's differences between ensemble members, of course, revealing the uncertainty that's associated with the parameterizations and the climate projections. So to quick summary, we're combining understanding of future hazards in the UK with exposure and vulnerability information where possible to try and understand risk to UK sectors. These are just a quick couple of starter examples of case studies we've been working on initially. So we're building them up and also aiming to include more advanced statistical methodologies in the future as well. Our approach is really dependent on building links with stakeholders, and our intention is that the research is fed back into decision making for UK climate adaptation. So thanks very much. Please do not hesitate to get in touch with me. I'll be working on this topic for a few years and would love to build some more collaborations, and it's great to have this network and webinar series. Thank you.
Thank you, Freya. This was a really interesting overview about what's going on in the Met Office on this topic, especially like your example for the preconditioned event. Yeah, so the paper will come out on the 15th of June.
Okay, great.
So are there questions? Again, please just use the raise hand. Zheng Zhao, do you want to unmute yourself and ask the question? Zheng Zhao, you're free to speak.
In case you have issues with the sound, Zheng Zhao, maybe you can type in the question in the chat. Seems like we cannot hear you.
Okay, the question is about the projections. Of cool spring and hot summer. And the question is whether there's a physical mechanism for this.
Oh, well, so in 2018, it was quite an exceptional event. To get into the drivers, obviously, if we get a very cold winter, we tend to be getting more prevailing conditions coming down from the Arctic. And then the hot, dry summer. Well, a lot of people, I think there's a few different mechanisms that kind of fed into that, but it was possibly, it could just really be the way the sort of jet stream blocks in for certain periods of the season. So under climate change, we might see more blocking like that. So if you get the conditions where the sort of blocking is such that in the UK or Northern Europe, you get more Arctic type conditions in the winter, then and more continental hot in the summer as well, then you get that sort of combination. So it could be a bit of the climate change effect of maybe increased blocking causing longer duration periods of that, and then some of the internal variability over different years as to what sort of conditions you get. And obviously things like the climate variability, so indexes such as the NAO and AMV will play a part, and sometimes as those things combine you get exceptional conditions.
Thanks. Yeah.
So do I anticipate any benefits of the multi-compound information to the agricultural insurance sector? Well, I hope so, actually. So the insurance sector does a lot of work on sort of catastrophe modelling and things, but I think it can be difficult to make relationships between our academic type research and insurance companies sometimes, but it would be a great to link that up a bit more, because I think even our research communities could probably learn a lot from the type of modellings that the impact modelling that the insurance sector uses. Appreciate that doesn't really answer the question, but hopefully it is something that we can continue to increase those links, and yes, they hopefully would be interested in that information.
I mean, these events that you're looking at, they're quite complex, you could say, right? What is your intuition? How dependent are these statistics on the model you use? And are you planning to explore this a little bit?
Yeah, so obviously for regional modelling, there's a limited number of models, but hopefully, with projects like the Cordex, Eurocordex, and EU climate projections, there'll be some overlapping regional models that we can then compare against. And then there's things so I look at the UK average, then I can obviously compare to a lot more multi-model ensembles, like through our probabilistic projections or even through direct comparison to CMIP5 and CMIP6 type models. So yeah, that is something I'll be trying to draw in to try and give a better evaluation of the uncertainty.
Thanks.
So there's just a quick one about thresholds of impact of agriculture. So yeah, it's a physical consideration as well as So the threshold of that I've shown were for the heat stress was a sort of demonstrated known physical one, and then I've used the one for cold spring, warm summer from the index of the extreme event from 2018, where we know that the impact was quite large, so that's also physically based as well. So yeah, it's I still might use statistical ones in some cases, but where physical information is there, we want to try and draw that in as well.
Okay, thank you.
Thanks very much.
We have to move on. Thank you, Freya. Now the last talk is by Mohammed. Can you start sharing your screen? Yes. Great. So we'll unmute you. Now you should be able to speak.
Okay. Hello, everyone.
Yep.
My name is Reza, and I'm an assistant prof at Western University in the city of London, which is not in the UK. It's in Ontario, Canada, close to the city of Toronto. So this work is part of my master's student research work. Harry, who is now working in Ocean Networks Canada, and as part of his research, he was looking at the covariability between temperature and precipitation. And as you know, these are the two main variables that can affect weather extremes. If you consider, for example, low temperature with precipitation, it could cause heavy snowfall, freezing rain that can cause power outages, or scenarios where we have wet conditions, which under warm scenarios, that can result in flooding, like rain and snow events, which are quite common in Canada. Or scenarios where we have dry conditions in hot days that can facilitate or cause wildfires and droughts. But these issues are quite common in Canada. And in recent years, we have seen a lot of them. For example, we have seen heavy snowfall events in British Columbia, Saskatchewan, Manitoba, and recently in Newfoundland that has caused some issues, as well as freezing rain in 2018 in Ontario with lots of power outages. We also have had and continuously have problems with rain and snow events that cause spring flooding, including in the city of London, as well as wildfires, which are quite common. We recently had flooding in Iran, and we also had in Australia. Similarly, we have continuous wildfires in Western Canada, especially the one in 2016 in Fort McMurray, which was the most the costliest natural hazard in Canada. So we started looking at the temperature and precipitation covariability. The figure on the right shows that the red dots are based on the observed records, and you can see for northern latitudes there is positive relationship between these two variables, meaning that if you look at the seasonal or annual scales, with increases in temperature, we expect to see increases in precipitation. However, this relationship is varies spatially, and in areas close to around the prairies, we see there is negative relationship, meaning that with increasing temperature, we expect to see dry conditions. So these are more suitable for warm and dry situations. Now, what I'm going to present is mostly focused on changes between this covariability using the copula functions, and to see how climate change plays a role in basically changing both each of these variables as well as their interrelationships in the future, and how can they affect our wet and dry conditions. So we use the three large ensemble climate simulations from a Canadian regional climate model called CanRCN4. This is about a 0.5 degree climate model from 1951 to 2100, and it generates 50 ensemble members. So Alex Cannon from Environment Canada, he developed a multivariate bias correction approach in 2018, and he used that method to bias correct both temperature and precipitation by maintaining their interrelationships as well as bias correcting their marginals. And these two new data sets are bias corrected based on two different reanalysis products, EW-ENBI and S14FE, and they are called Canadian Large Ensembles Adjusted Data Sets. I think the paper should be submitted soon for these products. So we call these can leads. So in this research, we looked at these three large ensembles. One is the raw Canard CM4 data, and the other two are the bias-corrected data based on two different observation data sets. So our objectives were to assess the RCM biases before and after applying the multivariate bias correction, and to characterize the spatial and temporal variability of both temperature and precipitation extremes under different warming scenarios. And more importantly, or I should say something that was very of great interest to us, was to see the influence of the dependency structure between temperature and precipitation by isolating the effects of the marginals on future compound warm wet, and warm dry events. So looking at the univariate biases, the figure is showing the seasonal bias of the maximum temperature for, I think that's for winter. The figure on the left is Canard CN4. We see warm biases from northwest to southeast, and cold biases in the higher latitudes. The Canley products both have significantly reduced these sorts of biases, but still we see some overestimations on the western coast, and some cold biases on the higher latitude. Precipitation is quite varied, and this only shows the result for winter. However, the results vary quite a lot between seasons. And the performance of the bias-corrected products, although there are some improvements in some locations, but in some locations we also see the improvements is not much. Even sometimes we see the overestimation has turned to underestimation. So, the result is not as promising as temperature, but still we see some improvements in the precipitation biases. Now, the intention is to look at the precipitation and temperature covariabilities. So we wanted to see how these products maintain the interrelationships between the two variables over Canada. So the figure on the left, and I should also mention that we use the Anspline product, or the NRCan-net observation, gridded observation data, which is quite widely used in Canada. It's based on Environment Canada gauge data. It's a 10-kilometer data set, and we aggregated, we regridded all data sets for 0.5 degree cell. So the one on the left is based on the observation, and it shows a warm, dry, warm, wet, and dependencies, and areas where there are no significant dependencies. And again, this is for winter. Sorry. And most of the areas show warm, wet dependencies, meaning that with increases in temperature and the tails of temperature, higher tails, we see increases in higher tails of precipitation in winter. And but the prairies has a different situation. The red area shows that it has a negative dependency leading to warm, dry conditions. So these are based on the observed data. Now, if you compare the simulations with our observations, the figure on the right shows the number of grids that have warm, wet, and warm, dry biases, warm, dry conditions. This happens a lot, right? So we compare our simulations, Canard CN4 and Canley, with our observation, and in general, they show close relationship. And by the way, this is based on the goodness of fit test proposed by Genest in 2006. So overall, they maintain spatially, they maintain the interrelationship between temperature and precipitation. There is a minor, slightly better consistency between the candidate bias-perfect products as expected with the other compared to Genest and raw data. All right. We further use the hierarchical Bayesian model proposed by Tebaldi in 2009. So this model basically generates the joint distribution of temperature and precipitation, and we can also project it into the future. It estimates the correlation between the two variables and the piecewise linear trends, and also assumes that there is a normal bivariate distribution of temperature and logarithm of precipitation. So we use this approach because it gives us the projections of precipitation and temperature in the future, as well as the biases of each of the ensemble members of each ensemble compared to our true posterior distribution. So the continuous line or distribution shows the posterior distribution of the historical period, and you can see the uncertainty down. And the ensemble members are shown by small bars. So if an ensemble member is closer to the mean of this distribution, obviously the bias is less. So for this case, for temperature, we see larger variation in terms of for CAN-CN4, lower variations and more accurate estimations for candidate products. And we see a sensible increase in temperature in the future. And by the way, these are decadal averages. And I'm just showing the decadal average centered on 1995 for the historical period, and the decadal average for 2095, centered on 2095 for the future. On the figure on the right shows similar plot, but for precipitation, as you see, and as we also noticed for plot bias maps, the improvement is less significant compared to the temperature. We see some uncertainties in the candidate products. And by the way, these are the marginals of marginal distributions of both temperature and precipitation. So this is basically how the hierarchical Bayesian overall works. And using this approach, we can also see the projected changes in temperature and precipitation. So the control lines are showing the bivariate distributions of the two variables. The blue one is over the historical period, and the red one is over the future period. And this is for a region in eastern coast of Canada. So when the control line moves to the right and up, it means that we tend to have warmer and wetter conditions in average, decadal average. So as you see in most seasons, we have this trend in this region, which is spatially average in Canada over the future, except for the fall, which we see quite negative trends. Similarly, we looked at the western part of Canada, similar trends, higher temperature trends, and trends to have wetter conditions. Now, the situation for the prairies also shows increases in temperature and precipitation average, but decreases in the summer, which is consistent with the recent Canada climate change report in 2019. All right, so these changes are the result of both changes in the temperature and precipitation individually, as well as changes in their interrelationships in the future. Now, our objective, our third objective was to separate these two and to see if we can single out the effects of the marginals and just focus on the dependencies and see how changes in those dependencies can affect the joint return period of a compound warm-wet period or a compound warm-dry event. All right, so our focus, so that's why the large ensemble turned out to be quite useful for us, because now for each ensemble we have 50 members, 50 realizations from our cohesive planning system from the same model with the same structure. So just as to briefly explain how we did that, let's consider each of these ensemble members from one of the ensembles. And we have 50 ensemble runs for temperature and precipitation. We took blocks of 3 years, and in each block we took the seasonal data, average temperature and accumulated precipitation. So for each block, for each ensemble run, we have 3 data points for temperature and 3 data points for precipitation. We have 50 ensemble runs, so 3 times 50, we have 150 data points if we pull all those data points together within each one block. So if we do it for the first block, we have 150 data points of temperature and precipitation. And we can look at their interrelationships. Similar to our observed plot, we can plot them to see if there is any positive or negative or no dependency between them. Then we move this block another 3 years, and until the end of the 21st century, we will end up having 50 blocks of 3 years. Now, each of these blocks have different interrelationships. To single out the effects of the marginals, for each block, we focus on the 90th percentile of the both temperature and precipitation. So if we consider this joint return period of, let's call it and, having temperature exceeding the 90th percentile and precipitation exceeding the 90th percentile for warm, wet, for example, scenario. For dry condition, we use negative P. So f of x and f of y remain 0.9 in all cases. But the thing that changes is this dependency within the copula function. If they are independent, it's just it's simply the multiplication. Otherwise, we have the value from the copula. Now, this figure basically summarizes the results. The line, the horizontal line on the top is the independent scenario where the return period for example, one dry season is always 100 years. The blue line is for the observation NRCan net for 1951 to 2000 by considering the effects of, by considering the interrelationships between the two variables. And as you can see, the return period is reduced, meaning that by considering this dependency, we have a more reliable estimate of this event, showing that it's going to happen more frequently. And these dots are the results of our ensemble simulations for each block. So we have 50 points, and each point represents one of the 3-year blocks, starting from the historical to the future. This uncertainty bound comes from the Bayesian copula. Now, what it shows that is that if we assume that there is no change in temperature and precipitation extreme, and the only change is the result of the interrelationships, there is a significant trend, and there's a change from, let's say, 50 to 40-year event just by considering the interrelationships. There's also some differences, of course, between the observation and simulation, which varies spatially. So that was quite interesting for us. We can do that for any ecozone in Canada. This is for one of the ecozones in the prairies called boreal plains. Again, we see more frequent extremes, and similarly for other regions for each of these ensembles, we can see changes in extreme conditions, where dry conditions, just by changing the dependencies. The event doesn't necessarily become more frequent. Some ecozones show weaker interrelationships into the future for both warm wet and warm dry conditions. So most of the results that are presented here are submitted in a paper, in 2 papers that are in review and are not yet published. So as a conclusion, I just wanted to highlight the importance of generating and also applying the climate data products that can maintain the covariability between, in our study, temperature and precipitation for the analysis of compound weather events. We found that the large ensemble simulations are quite useful and allow for the assessment of projected changes in compound events by singling out the effects of the marginals and focusing on the interrelationships between temperature and precipitation. There was strong non-stationarity in the dependency structure of the 2 variables, which suggests that these should be considered in climate change studies. If we focus on extreme temperature and precipitation isolation, we will certainly end up underestimating the compound warm wet and warm dry events. And finally, NRCan-Met was the basis or the reference data in our study. However, several studies, including our previous study, have shown that the biases exist in observation data as well, including biases in its covariability. And by that, I end my talk. Thank you.
Thank you. It's an interesting application of the use of single model large ensembles for compound event research. There's also a webinar series now starting on these type of large ensembles next week, I think. First talk is given by Clara Deza on Monday. So are there some questions to this talk? I can see Bart. I don't know. Okay, Cheng Shao asked again. In page 9, there's an increase of temperature and decrease of precipitation from 2000 to 2100, considering the positive precipitation temperature dependence in the majority of the area. How do you explain this feature? In addition, from the Clausewitz-Clapeyron relationship, should we see a concurrent increase of precipitation and temperature, particularly in this high latitude region?
Okay. All right, so let's go back to the question. Thank you for this question. So there is increase in temperature and decrease in precipitation, considering positive PT dependencies in the majority of the area. How to explain this feature? All right. So the figures that I showed are for, I basically picked some figures because I couldn't include all of the figures in this presentation. So the results of, for example, one is not really comparable to the other because the seasons might change. However, let's consider we have a region that shows a positive or negative precipitation temperature dependencies. And one would ask if there is this negative dependency, then we should expect to see increases in precipitation in the future, or if, for example, if there is a positive relationship between the two, then we should expect to see increases in precipitation in the future because there are increases in temperature in the future. However, this is not really the case. I can give you the example of the prairies. In the prairies, there is negative relationship with most seasons, but if you look at the decadal averages, you see an overall increase in most of the seasons except for the summer. So yes, there is seasonal dependency. If you look at the seasonal data, there might be positive or negative dependency, or annual data. But if you look at in average, 10-year average, 15-year average data, with increasing temperature and the amount of moisture in the air, that doesn't necessarily mean that positive or negative dependency will translate into increases or decreases in the future. However, we definitely see influences of such dependencies on extreme conditions like warm, dry conditions. So yeah, so that's partly the case. The other thing is that the rate of change of temperature, as you see in this figure, is much more than compared to the precipitation. So from the CC relationship, should we see a concurrent increase of P and T, particularly in this high latitude region? We had a paper published recently on looking at the CC relationship using historical data. And in most of our areas, we had this increase of precipitation with temperature. In some areas, I think, as you mentioned, in higher latitudes, as far as I remember, it was super CC. We noticed rates more than 7%. In some areas, it was much less. It was about 2 or 3%. So yeah, I agree with you that we should expect to have more intense precipitation with increasing temperature. I hope it answers the question. All right. So does a change in the dependence structure lead to a conclusion that the persistence of weather patterns bringing dry, warm air into this region is increasing? Yeah, that's a very good question. I think that's partly the case. I think it's a very interesting idea that's definitely worth looking at, especially where we have warm, dry conditions and the dependencies are becoming stronger. So we should have this persistence of the patterns. And that's something that we should definitely consider other variables of our climate model, and to see how these large scale patterns can lead to stronger or weaker dependencies in the future. But that's a very interesting idea.
I've also worked a bit. Maybe I can comment on this question as well. I've worked a bit on this question, and also found this increase in dependence, especially in summer, in high latitudes. And one hypothesis that I would have is that it could happen that in high latitudes, if you get then warmer temperatures overall, you decrease soil moisture earlier in the season because of higher evaporative demand, for instance. And then in summer, you have stronger soil atmosphere feedbacks that then lead to higher, to more dry and hot conditions, basically. But that's also not so easy to verify, I think. Bart is still. I unmute you, Bart. Can you speak?
Yeah. Thank you for allowing me to speak up, because I'm really intrigued by this change in the dependence structure, even for stationary temperature and precipitation fields itself, and it has to be some kind of a dynamic imprint, if that is. And it would be interesting indeed. Two things. You could maybe explore, say, the distribution over time of the joint occurrences of these extreme conditions, whether they are grouped in the same time window or just scattered around the entire record is probably of interest. So more like an autocorrelation type metric. And also Jacob's suggestion also is very good. There's a good reason to believe I'm now in Europe and we are experiencing again a very dry spring season, and again without any precedents. And if you think about droughts in this area, which indeed can induce a positive land-atmosphere feedback that leads to drying, there is most prospect for intensifying droughts in our say mid-latitude regions is probably in the spring season. And that is where the typical have, of course, there is a seasonal cycle in precip that is not very pronounced. It is, we have precip all over the year. There's a bit of a seasonal cycle, but of course, the seasonality comes in the evaporations part. And it's in high summer, it's very difficult to make a dry season even drier. But in the spring season, when evaporation kicks in earlier in the season, there you can really see pronounced climatological changes in the occurrence of P-E shortages, so to say. Mm-hmm. And it's also interesting to see if you see a seasonal shift of that correlation structure over time.
No, that's a very.
And that would indeed extend your typical dry season a bit further forward in time. I would say rather in spring than in autumn, because in autumn you already have, say, the delayed dry season where there is only very little space for the hydrological budget to move around. But it is in the spring season where climatologically there is quite a bit of moisture still available in the area. There is also room to maneuver between dry and wet episodes, much stronger than in autumn.
Yeah, it just give me the idea. Maybe we should also look at the aridity index.
Yeah, something like that. Yeah, and typically we measure these kind of things with SPEI, and then you accumulate over a seasonality or over a couple of months. But that also you really should be very careful and synchronizes with seasons. It's more a seasonal signature than a length signature, I would say. So an SPEI runs the risk that you mix up autumn and spring numbers, and that you actually blur the signal. You really have to synchronize and lock into the seasonal cycle.
Thank you. Good suggestion.
Related to the dependence discussion in your slides 16 and 17, it looked a bit as if the observations are actually quite far away from the model dependence. Is it correct?
Yeah, it is quite varied.
So did you look at, did you quantify this a bit in which regions you overestimate or underestimate the dependence with the models?
Yes, we have I don't have the values here, but all of these are generated for all of the ecozones in Canada. And we have all the biases. For example, in this region for where I'm located, region 8, which is called mixed wood plains, there's more consistency. Yeah. Canada CN4. But Canada products show some overestimation.
Do you know how good the observational data is that you're using here? Is this
that's the main thing?
Because that's actually what I found also in this type of evaluation.
Yeah.
That at the end,
so if I because we also had a study comparing the different observation data. We used the NRCan Met, compared it with these multivariate analysis products. And overall, for univariate case, for example, for temperature and for precipitation, biases are, we compared it with the most reliable gauge data that we have in Canada. They're called AHCCD data. They were quite good, but in terms of the covariability, it didn't really differ much from the other products. So there is also the problem with our observed data.
Yeah, so what I saw is that in some of these observation-based data sets, when you don't have a station nearby, especially for precipitation, this is a problem often. You just take the mean seasonal cycle, and then of course you destroy the covariability. So you reduce the covariability, and then you cannot do the comparison with the model. So you should only compare in regions where you know that the observational database is good.
This problem is mostly significant in the Rocky area. Western Canada.
Good. Interesting discussions. Are there any more questions? We are reaching 90 minutes also now. So we can also stop here. Kai, maybe you want to announce. So I would like to thank all the 3 speakers again Maybe Kai has an announcement for the next webinar.
Yeah, thanks again also from my side and the risk-can compound extremes working group. We will have an upcoming webinar on June the 30th. The confirmed speaker so far is Michael Puma, who will talk about COVID and risks to food security. We will announce that webinar again over our mailing list, which you can join in case you are not yet a member when going on the risk-can webpage, which is risk/can.org. And yeah, I guess with this, I say farewell and see you next time.
Thank you very much, everyone. And see you next time.